In this question, we're trying to find the gravitational field strength of the Earth at the Earth's surface and 2,000 meters above the Earth's surface. So it would stand to reason as we get further and further away from the Earth's surface, the effects of gravity would become weaker and weaker. So we would expect that when we're 2,000 meters above the surface, our field strength will be a little bit smaller. Let's start by defining what gravitational field strength actually is. Gravitational field strength for us is the same thing as little g. So we've been calling this the acceleration due to gravity. It's also known as the gravitational field strength. So let's think of it in terms of the acceleration due to gravity and see what we can do with this question. Now we're right at the surface of the Earth. So imagine we're just a tiny little mass just above the surface of the Earth, somewhere like this. And that mass is experiencing some sort of acceleration due to the force of gravity. So the only force that's acting on that mass as it falls is the force of gravity. So that must be our net force. So right when we're at the surface, our net force is Fg. Now we know from Newton's second law that our net force is defined as ma. And we also know that our universal equation for gravity is capital G, the universal constant, times m1 times m2 all over the distance squared, or r squared. R is the distance between mass 1 and mass 2. These are the two masses that are causing the attraction. In this case, one of the masses is our little falling object, which could be anything, and the other mass is the Earth. So those are the two objects that are attracting each other together. So we have a mass on either side of the equation, and they cancel. This mass over here is the one that's accelerating. So I've defined it as mass 1. So the accelerating mass cancels, and I've got an expression that says the acceleration caused by gravity is capital G m2 over r squared. So in effect, I've figured out what little g is, because remember, little g, the gravitational field strength, is the acceleration due to gravity. So all I've got to do is go g, mass of the Earth, all divided by how far away from the center of that object we are. Remember, in my original equation, g m1 m2 over r squared, r is the distance from the center of m1 to the center of m2. So on a big scale, it looks like this. There's the Earth, there's the center of the Earth, there's my tiny little mass on the surface, and we want that distance from center to center. Now, if this object is really, really tiny, that would simply be the radius of the Earth. So if we're trying to find the acceleration due to gravity at the surface of the Earth, also known as the gravitational field strength, I simply put in my constant, 6.67 times 10 to the negative 11, multiply it by the mass of the Earth, 5.98 times 10 to the 24 kilograms, and divide it by the radius of the Earth squared. 6.38 times 10 to the 6, all squared. And when you do the calculation, that's where we get our familiar number, 9.8 meters per second squared. That's at the surface of the Earth. So we've got this sort of shortcut that'll help us figure out the gravitational field strength at any location right here. So now when we skip to the second question, which I'll do in blue, the second part of this, we already are halfway there. Now we want to figure out the gravitational field strength when we're 2,000 meters above the Earth's surface. So I'm going to exaggerate this. Here's the Earth. Now my mass is somewhere up here, and the distance from the center of this object to the center of this object, right here, will be the radius of the Earth plus 2,000. So that's what we're going to put in our denominator of our equation. So when we solve for this one, we go little g equals g, mass of the Earth. Remember, the mass of the object that's in question cancels off. The object that's accelerating cancels off. So capital G, mass of Earth, all divided by r squared, where r is how far away from the center of the Earth we are. This could be any planet, by the way. So we go through the calculation, and I get 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24, all divided by radius of the Earth, 6.38 times 10 to the 6, plus 2,000, because I'm a little bit further away now, all squared, and I get almost the same answer, just slightly different, 9.79 meters per second squared. So 2,000 meters isn't that far. Mount Everest is 8,000 meters, and we know that gravity doesn't go away at the top of Mount Everest. So it takes a reasonable amount of distance before gravity starts to fall off. The gravitational field strength starts to fall off substantially. So when we're 2,000 meters above the surface of the Earth, it's a little bit weaker, but not much.